Yes, thank you for the introduction, and let me thank the organizers for giving me this chance to present our work here. So I'll be talking about a project we started with Frank den Hollander, Michel Manches from University of Amsterdam, Andrea Roccaferre from Leiden, and myself, and it concerns implementing some models from statistical mechanics into random graph theory, and more precisely, studying this ensemble equivalence in dense random graphs. So my talk, I will start with a general introduction and then motivate our research, and then I would like to place and to position our results in a general framework, what has been done in this class of models. So I will present a little bit a general overview of what has been done and what is our contribution in this big theory over ensemble equivalence and these random graph models, and then a little bit more details about our results. And then I will spend some time on some ideas and some things we would like to do in the future. So here, this is still work in progress, so it's just some ideas how we can proceed and what should we prove. And then in the end, I added a literature review for someone who is interested to have a look at the slides. So to start, what we are interested in, we consider graphs labeled undirected on n vertices. We will use the standard notation. A graph G will belong in this space of all possible configurations on n vertices. And what we are interested in observables. You are looking some network and then you observe some quantities. We'll call these quantities constraints. And you can think of a simple example where you have number of edges and number of triangles in your network. And we will usually express these observables in terms of some density, so a fraction of the total number of edges and a fraction of total number of triangles. And I will consider this model of edge and triangles because this is the most simple model which has a rather complicated behavior. And in general, what we do, you can also consider more general constraints, but I will keep it on this simple framework to make the notation a little bit lighter. So in general, as I said, our observable or our constraint will be a function from this space of graphs to Rm. So this is in general called the graph parameter in the literature. And at the first part of my talk, this will be independent of n. So a graph parameter, for example, the degree sequence is not, we will not consider parameters like the degree sequence at this moment. So let's see, on this space of graphs, we introduce two probability distributions, two probability measures or ensembles in the following way. So we have the uniform probability measure or else microcanonical, where on graphs, on a graph G, we assign uniform probability mass if this graph is in this set. So this is a set of all possible graphs which satisfy the constraints that we are imposing, which satisfy the constraints. So we see from the beginning that in order to study this probability measure, it's essentially a counting problem, counting graphs which have a specified structure. And then the second graph is this canonical ensemble or the exponential random graph model probability measure, which is actually a parameterized measure. It has some parameters, theta 1, theta 2, depending on the number of constraints you impose. And it has this form. So here you have this partition function, the normalizing constant, and this exponential form. And this probability measure, there is a whole theory behind it. How do you get it? And this theory about this exponential random class of models was first introduced in this paper, where you use a maximization of entropy with respect to some constraints in order to derive this formula, this expression. And so here you have some general parameters, but we are interested in a specific choice of parameters, namely theta 1 and theta 2, star, which yield these desired averages. So on the canonical ensemble, we choose these parameters so that on average, you have the observable, you obtain this constraint, but in the microcanonical ensemble, you just fix them from the beginning.
So, one question?
Yes?
So in the microcanonical, do you take with symmetry, or I mean, are the vertices labeled or unlabeled?
They're labeled.
They're labeled.
Yes. Yes? Yeah, so the constraints, so these are some, so you start with such a graph parameter, and then a specific value of this graph parameter, you consider it as a constraint on your graph. No, I didn't specify it yet. So it's just, let's say, a specific edge density and a specific triangle density. Does that answer the question? Sorry? So here. Yeah, so if in general, this canonical probability measure, it's the partition function and exponential of a Hamiltonian. So that's how is the original form of this probability measure. And this n squared comes because we are interested in dense graphs. And in dense graphs, you know that the number of edges scales like n squared. And then in order to be able to get meaningful expressions in the limit, you have that this whole expression of the Hamiltonian should scale like n squared. And we will see later on, it will become clearer later on when we will see how this probability distribution behaves by using the large deviation result, that the n squared is actually the scaling of this exponent. And essentially, if you write things down, you can see that if it should be n squared, because if it's less than n squared, then you're not in the dense regime, and otherwise you get trivial results in the limit. So, yes.
So T1 is specifically the number of edges?
So here in this, oh yeah, sorry, I didn't specify this. So when we write here, T1G is the edge density in a graph, and T2G is the triangle density in a graph G.
And this T is some other observable, or it's one of
which T? This T?
Yes.
Yes, so now, so we have a graph, so T1 and T2 refers to edge density and triangle density, and when I write T, I mean a fixed constraint, a fixed edge density, and a fixed triangle density. So this bold T is a vector T1, T2, so the bold T is a vector of edge density and triangle density. And when I write star, T star, I mean a fixed constraint on the edge and triangle density. Yes. Yes, so by density I mean these numbers. So this is the total number of edges that a graph can have. This is the total number of triangles a graph can have. We want it to be dense. So this, we have a constant fraction of edges and a constant fraction of the total number of triangles, which we denote by T1 star and T2 star. Yes? Yes, so in the dense regime, we know that the number of edges scales like n squared, the number of triangles scales like n third, and this is a constant fraction of this parameter, of this constraint. Okay, so this is the setting. These are the two probability ensembles we will look at. So in general, this has two free parameters, but we are interested in a specific choice which realizes on average this constraint on the edge and triangle density. How do we compare these two ensembles? We use the relative entropy, which is defined in the following sense. So the relative entropy between the microcanonical and the canonical ensemble is defined like this, and essentially you can also study other, for example, you can also study the total variation distance because of an inequality with the relative entropy. And always in the dense regime, if this relative entropy in the limit with this scaling n squared is equal to 0, then we say that the two ensembles are equivalent. And to say something more about this, so this idea of ensemble equivalence, at least I got familiar with it from this paper, Hugo Touchet, where it was firstly introduced. And in the beginning, the original definition we have here is scaling of n1 divided by n. But because we are studying in the dense regime, we saw that also with the scaling of n squared, you can identify regions where this relative entropy is positive. So in the beginning, we thought that with a scaling of n squared, this should always be 0. But because all the examples we had a scaling of order n, but we found out regions where this relative entropy in the limit is also larger than 0, also with this scaling of n squared. So the motivation behind what we actually want to achieve by looking at these ensembles and the relative entropy is we want to characterize this relative entropy S infinity. And then we would like to find, let's say, a general rule when does breaking of ensemble equivalence occur, if it occurs, with this scaling n squared, or determine the constraints. Now we saw this edge and triangle density, determine the constraints and the values of these constraints, the specific values or regions of values of these constraints where the relative entropy is positive. And if the relative entropy in the limit is 0, until now with the scaling of n squared, then find the scaling where this is positive. Let's say what happens with the scaling of order n or log n. So let's start with with the canonical ensemble. So in general, the canonical ensemble or exponential random graph model in most of the mathematics paper is defined in this form, at least for dense graphs is defined in this form, where you have the partition function, and here you have the number of constraints, where this can have a more general form, but in our model, I will call this, let's say, the edge triangle model, we have this form. And in general, the canonical ensemble has here the Hamiltonian, where in the model you're looking, you specify it. We'll consider now this form as the canonical ensemble, and one of the first papers of Bamiri, Bressler, and Sly, they looked at mixing times of exponential random graph of this model, and they found out that essentially in the limit, there is a region of values where you have Erdos-Renyi type of behavior. So they have this theorem where they say that consider this function of the parameters, of the free parameters, and suppose that the edge parameter is real and the triangle parameter is non-negative. And then if you find, if this function has a unique fixed point, call it P star, then in the limit, a graph drawn from this probability measure is indistinguishable from an Erdos-Renyi random graph with this parameter P star. So this is the first result that they derived in this paper, and they used Gaubler dynamics in order to prove this. And by using Gaubler dynamics, they don't actually need to bother about this partition function, and they can find this, this result for this range of parameters, although, and they also distinguish the case where you have more than one fixed points. And this result was generalized by Chatterjee and Diaconis, where they used large deviations results to study this exponential random graph model, this canonical ensemble, and one of their first, they managed to find an expression for the partition function, actually the logarithm of the partition function in the limit, and they managed to find an expression for this quantity for all possible values of your free parameters. So for θ1, θ2, all real numbers, they managed to find a variational formula for this partition function. And for the case that Bamiri also considered in his paper, so if θ2 is non-negative, then this reduces to this supremum over the unit interval. And from this, actually, you can see that any solution of this variational formula has to be a fixed point of this function, because the fixed points of this function are just stationary points of this expression here, this function. And here is the question, and this function I, as we will see later, is given by this formula. And they have this theorem when we say a unique maximizer. If this has a unique maximizer, then you have Erdős-Rényi behavior with this parameter. Otherwise, you have a convex combination of Erdős-Rényi graphs in the sense that it's Erdős-Rényi, but with a random parameter chosen at random from the maximizers of this quantity. But in any case, they managed to identify the structure of these graphs in terms of Erdős-Rényi. Yes? These two? Which? Theta 1 and theta 2 are the free parameters of the canonical ensemble. So the one corresponding to the edge constraint and one to the triangle constraint. Theta 1 is the edge constraint and theta 2 is the triangle constraint. Yes?
I of u, so this looks like a little bit like this large division for this line.
Yes. Yes. Yes, I will show it in some slides. This is the large deviation. It is actually the rate function that Varadhan and Chatterjee define. So Chatterjee and Diaconis, they also observed that there is a phase transition canonical random graph in the canonical ensemble in exponential random graphs. This was also previously observed by other authors, but they managed to prove that. Now, they actually did some numerical results, and they have shown that if you define this function, so the maximizer of this quantity that we had in the variational formula as a function of theta 1 and theta 2, for theta 1 sufficiently small, so for negative theta 1, then this function has a discontinuity in theta 2. And then Radin and Yin, in a paper, they managed to explicitly find the regions where phase transition happens and exactly the values where this phase transition happens. And then Yin also studied more general models and the edge triangle models to identify these phase transitions. So this phase transition is actually a really interesting subject and makes estimating these parameters from observables really difficult. And after all these papers, there was an enormous production of papers on this phase transition and exponential random graphs. So how did they actually manage? In Chatterjee and Diaconis, they relied on Graphons in order to prove the results. And here I'll go a little bit quick through the general theory, what is Graphons. So essentially it's a natural way to write a graph as a function on the unit square. So you start with a graph and you define a function like the adjacency matrix. You write it as a step function on the unit interval. And then in this way you can embed all graphs in one space of functions which contains functions from the unit square to the unit interval, and they are symmetric. And then you can define a topology, convergence on this space. So you say that the sequence of graphs converges to a graphon, a function, if for every finite simple graph H, you have this convergence of the subgraph of these subgraph densities. So a graph converges to some function if all its subgraph densities converge in this sense. So I don't want to spend a lot of time on this. It's just an intermezzo, as it says. So you can define on this space a metric, the cut distance metric, which actually this whole theory gives the right tools in order to derive large deviations result and these variational formulas. So you define a distance on this space of graphons. Okay, so intuitively this means that you take a graph, you partition it into two disjoint sets, and then you study the largest cut set. So you study the largest set of edges which go from the one disjoint set to the other one, and then you define this metric in this sense. And now we are ready to show the large deviation principle on this space. You define a probability measure on the space of graphons by using the Erdős-Rényi probability measure on this space of graphs. How do you do that? For a set in W, you just define this probability measure, on a set F, and Varadhan and Chatterjee, they proved this theorem in 2011, so the large deviation principle on this space. And here you'll immediately see the emergence of some tildes here. Don't bother about this. So this is just a technical adjustment to take care of isomorphisms of all these quantities. And so they managed to prove the large deviation principle, and they identified this rate function, which is essentially what you also said before, is this quantity here. So, and this is actually the building block of this whole theory. We rely on this to characterize both the microcanonical and the canonical ensemble to derive this variational formula, as we will see. So let's see how we can use this to study the microcanonical ensemble. So as I said in the beginning, we have this vector mapping from the space of graphs to Rm. In our case, it's the edge and the triangle density, this graph parameter. We define this set, all possible graphs which have this fixed value of this edge and triangle density. So T star was our constraint on the edge and the triangle density, and we consider graphs which realize this constraint, and then the microcanonical ensemble is just the uniform measure on this space. And now here we have to count the number of graphs that satisfies this constraint, and here comes the large deviation principle, because if this function T is a nice function, if it's continuous, for example, then it's easy to characterize closed and open sets in this Graphon space, and then we can use the large deviation principle to determine the logarithmic asymptotics of this quantity. And this is by taking the parameter p equal to 1/2, and then the Rosveni probability measure is just 1 divided by the total number of graphs satisfying this constraint. And there are some papers trying to find graph parameters which are continuous, and there is this paper where they identify various graph parameters which have this property, and subgraph counts are continuous, and this is not so difficult to show. So I have to say again that here your M does not depend on N. So for example, the degree sequence is not yet in the framework we consider here. Okay, so this is how we characterize a microcanonical ensemble by using the large deviation principle. And to go back to the canonical ensemble, we had this expression, T1 is the edge density, T2G is the triangle density, θ1 star, θ2 star are the specific choices of the free parameter that realize this constraint on average. And we see here that actually the starting point in our research is that instead of a general parameter θ1 and θ2, as it was considered until now, we start with a fixed constraints. So we don't know a priori what the parameters θ1 star and θ2 star are, but we know the constraints. So we have to find a relationship between constraints and the respective and the corresponding parameters. So, as I said, we want to compare the two ensembles by using the relative entropy with a scaling n squared. And we see here from the definition of the microcanonical ensemble, as it has been observed also in the past, essentially this microcanonical ensemble reduces to this expression where G star is just an arbitrary graph which satisfies your constraints, because you have here the microcanonical ensemble, essentially all graphs that do not satisfy your constraint yield 0 here. So that's how you get this. And this reduces this formula to a much simpler formula.
So this is almost sure?
Yeah, this is, yes. Yeah, almost sure. It's not in a probabilistic sense, it's just equal to this. It's not. So G star is just an arbitrary graph which satisfies these constraints. It's not So this whole sum, essentially, if you take, you only need to take graphs in Gn star, so graphs that fix this constraint, and then here, this is 1 divided by the number of these graphs, and the canonical ensemble essentially assigns equal mass to all these graphs that satisfy the constraint. So here, if you sum up over all these graphs, you just take this thing, the first term cancels, and then you take the logarithm. Sorry? It's not a particular graph, it's just an arbitrary graph which satisfies these constraints. It's not a specific graph. It's yes. Where? Here. It is, eh? No, because the sum actually reduces to only to this term, because if you sum over all graphs which satisfy the constraint, then you essentially sum identical terms, because the canonical probability distribution assigns the same probability mass on graphs satisfying the constraint regardless of the structure of the graph. And in this paper, the authors managed to identify cases where this relative entropy is positive with a different scaling, not n-squared scaling, with a scaling of order n. And they consider edge-related constraints. So, as I said before, our starting point is some observable, not these free parameters. So we need to make a connection between the observables, the constraints, and these tuning parameters, theta 1 star, theta 2 star of the edge and the triangle density. And this is actually the first part, what we did in the beginning of our research. So we try to make this connection. And for even more general cases, not only for the edge triangle model, you have that this theta star is non-negative if and only if the edge density is larger than a half, and this triangle parameter theta 2 star is non-negative if and only if the triangle density, the constraint that you impose on the triangle density is larger than an eighth. And these are the Erdős-Rényi parameters with probability p a half. And this is what we use in order to prove this. And if you have also other constraints on subgraph counts, then this can be generalized a little bit more. Yes. Sorry? What is that? The problem is that there might be a discontinuity, I think, at some point. But in general, yes, this is how you do it. You take the derivative with respect to the parameter, and then you put it equal to the constraint. But we didn't know, so the partition function is not a smooth function for all in the whole real line, for it. So now, let's see the main results. So we have this relative entropy. And using this, the large deviation principle and these results of Chatterjee and Diaconis, we could derive the following expression. So this, okay, it looks quite complicated. And again, these tildes appear, so don't bother about the tildes. It's just technical. We have to assume this in order to be able to use the large, not assume this. We need, this is the structure we actually need. But so this says that the relative entropy in the limit essentially boils down to studying these two variational problems. So you need to study, so this comes from the partition function of the canonical ensemble, and this term comes from the microcanonical ensemble, where you have here essentially the supremum over this W star of this function comes from counting graphs and using the large deviation result. And now there's a nice, there's a way here to see that this, if for example, the optimizer of this first variational formula satisfies the constraints, then automatically you get here 0, while this formula gives you a way to identify regions where this is positive or negative. And an additional thing is that by writing down Euler-Lagrange equations, you can show that all optimizers of the first quantity have to be bounded away from 0 and 1, and this is an additional feature that helps in order to identify regions of breaking of ensemble equivalence. And I have gathered our findings in the following graph. So let's take it step by step. What does this graph say? So this concerns the edge triangle model. So you here have the constraint on the edge density. I don't know if you can see the text, but I will explain it. So here you can see the edge density, and here is the triangle density. So let's take this graph without the colors and without all these regions. So what is this graph? So this graph shows you the area of realizable graphs given an edge and a triangle density. So if for this edge density and this triangle density you are on the boundary or in this curve, then this means that a graph with such a triangle density and edge density exists, that these constraints are realizable. If you are out here, it means that this combination is not realizable. So recently, this boundary here of minimal of graphs with a given edge density and minimal triangle density, the structure of such graphs has been recently it has been found in a paper. It was of 2015. And let's see, what does this graph say? So first of all, regions of ensemble equivalence. So this is the red line. So on the red line, we have that these two ensembles with a scaling n squared give relative entropy equal to 0. And what does this line? So the first red line corresponds to edge and triangle density equal to Erdős-Renyi parameters. So T2 star is equal to T1 star to the power of 3. So the edge density and the triangle density are a perfect match to Erdős-Renyi constraints. The line on the bottom means that you have some edge density but 0 triangle density. And then the two ensembles are also equivalent, and the graphs drawn from them both look like bipartite graphs. And then the blue curve and the gray region are regions where this ensemble equivalence is positive. And essentially, on this region, the microcanonical ensemble realizes the constraints, but the canonical ensemble in many cases tries to be Erdős-Renyi in some way, while the microcanonical, because you fix it from the beginning, is far away from the Erdős-Renyi structure. And there is a small region here, which is white, where we couldn't prove something about the relative entropy. So there is still a question mark here, which is a little bit annoying. So we keep working on this region here, and this actually, you see it's a region where the edge density is relatively high, but the triangle density is relatively low. So something is to be answered yet. Okay, so this shows a result concerning this edge triangle model. You can also do for similar analysis for more general models where you have also other kind of subgraphs, not only edges and triangles. And let me go now in what we would like to do in the future. So when you have this subgraph counts, there are still some open questions. For example, as I showed you, there is this region where we don't know essentially what happens, so we would like to investigate this a little bit further. But there is also, in this paper, Chatterjee and Diaconis, they also managed to identify a region, as I have mentioned until now, when this triangle parameter θ2 is non-negative, then things are a little bit easier to deal with, while when θ2 is negative, then things get a little bit harder to find the structure of the canonical ensemble, of the graphs drawn from the canonical ensemble. But Chatterjee and Diaconis, they managed to find a region of these parameters where graphs drawn from this canonical ensemble have an Erdős-Renyi structure, and this is when this inequality is met. And here we see that θ2, which is the triangle parameter, can also take negative values, and E of I denotes the number of edges in the corresponding subgraph. So if you have the edge triangle model, then this is θ2 times 6. So in this case, this has an Erdős-Renyi structure, and we expect, again, positive relative entropy in the limit, not 0, but it's interesting to try to identify exactly what the parameter should be, because now you're in a region where you can have a phase transition. And then also, actually, when we started, we wanted to do this for sparse graphs, but so this is also something we would like to do or to investigate in the future. So I will spend the last 2 minutes, if there are no more questions on this, in another idea we will have to work on the future, and this concerns constraints. I call them now global constraints and local constraints. So what I've seen and what I've studied until now, I call it global constraints, such as subgraph densities, so constraints which do not grow as the graph grows. So let's say edge, triangle densities, subgraph densities. So parameters of this form, a vector function into Rm, and I have some local constraints like the degree sequence, so a function from Gn to Rn. Or the triangle, I will call it triangle degree sequence, like this, where this is the number of triangles each vertex participates in. And here, there has been some work done by Chatterjee, Diaconis, and Sly, and they managed actually to identify a suitable topology and a suitable space where you can study these Graphons now, these limiting objects. And essentially, because now your parameter grows as your graph grows, essentially in the limit you get something like you get like an L1 function in some sense. So, and I will show a little bit what the idea is behind this and what our idea is, how we can use this. So for example, consider the degree sequence, and then this degree sequence grows as n, but it also scales as n. So you want to identify limiting functions which can be, what are the functions that can be used as Graphons to characterize graphs with a given degree sequence. And in that sense, you're working in a function space, in this modified L1 space, and the suitable topology of this space is actually given by this Erdos-Galai theorem, which shows, so this says that the given degree sequence is graphical if and only if the sum is even, and this condition is met. So, inspired by this, Chatterjee, Diaconis, and Sly, they managed to construct this space of functions that satisfy this constraint, and they say that these functions are essentially the suitable limiting objects of graphs that have the specified degree sequence. And now, the question is what happens for the triangle degree sequence, for example, which is more complicated and it's not linear as a degree sequence. So the first step is, can you find a condition which gives that the triangle sequence is graphical? So there is a necessary condition. So for example, if this is a graphical triangle, if this is graphical, if you know that it is graphical, then the sum should be a multiple of 3, of course. It's 3 times the total number of triangles, and this condition has to be satisfied. It's pretty intuitive. If you see the proof, then this condition is pretty intuitive, and but here, this is not sufficient. So you can have triangle sequences which satisfy this condition, but they're not graphical. But the question is, does this condition, for example, imply the right topology to work on? Maybe. So these are all ideas for future work. And let me stop here. Yes. Thank you very much.
In the cases where when there is no ensemble equivalence, when it breaks down, do you know anything about how the free energy looks like? Is it discontinuous?
Yes. So for the edge triangle model, when these parameters are positive, the edge and the triangle density, then this the solution of this is always this variational formula. Then the solution is a unique maxima, a unique point, and then there is a curve along which you have a phase transition, so you have a discontinuity, and this has been identified in this paper of Radin and Yin. But then, as you go to more complicated parameters, if you add one more constraint, then it becomes a surface, and then it becomes even more complicated phase transitions. So this has been investigated.
So along the phase transition line,
There are two. There are three cases. You have a unique maximizer. You may have two local maximizers, or you have a local and a global maximizer. You have two local which are both global, and then you can either have a local and a global. So there are these three scenarios for the edge triangle model.
let's say I don't care about the agents, we only care about triangle densities.
Yes, we did that as well. So if you consider only the triangle densities, then there are cases essentially when you have an Erdős-Rényi structure with a parameter, let's say P star, which P star third is your triangle constraint. But when your triangle density is less than an eighth and this parameter θ2 is negative, then it's more complicated to identify the structure, and that we couldn't do.
And the fact that you have an n squared always in the exponent for the canonical ensemble, is it because you have an order n squared edges?
Yes.
No matter, I mean, there's no n cubed for the triangle and an n
Yeah.
squared. It's because you have n squared.
There is
Order n squared.
order n squared edges, but there is also the number of triangles is of order n third, but the parameter θ2,
Yes.
it scales like 1 divided by n. So the total scaling is n squared.
Is always. So no, for usual subgraph counts, you will always have an n squared.
In the dense case.
In the
dense case, yes. Otherwise, you can show it that otherwise you get either trivial limiting behavior or.
Okay, so that's fine.